Welcome to Study Loop.
For this problem, on the topic of rotation, we are given a thin uniform rod in the figure, and the mass and length of which is given, and we are told it rotates freely about a horizontal axis A that is perpendicular to the rod itself, and passes through a point at a distance 1 meter from the end of the rod. We also know the kinetic energy of the rod as it passes through the vertical position. We want to calculate the rotational inertia of the rod about axis A, the linear speed of the NB as the rod passes through the vertical position, and the angle theta at which the rod will momentarily stop in its upward swing. So we know the moment of inertia using our tables and the parallel axis theorem is I is equal to 1 over 12 ml squared plus mh squared. Substituting the values in, this is 1 over 12 times the mass of the rod, which is 3 kg. L is its length, which is 4 meters, and that's squared, plus m, which is again 3 kg, times h, which is 1 meter, and that's squared. So calculating, we get the moment of inertia of the rod to be 7 kg meter squared. For the next part of the problem, B, we want to know the linear speed of the end B of the rod as it passes through the vertical position. Now we know the rotational kinetic energy, we'll call it K rotational, is a half times the moment of inertia I times the angular speed of rotation squared, omega squared. And this means that we get the angular velocity omega to be the square root of 2 times the rotational kinetic energy divided by I. We calculated these moment of inertia I, and we are given the rotational kinetic energy. So knowing the values, we put them in. This becomes the square root of 2 times 20 joules divided by 7 kg meter squared. And so calculating, we get omega to be 2.4 radians per second. So if we have the angular speed, we can now calculate the linear speed. So the linear speed of NB, VB, is equal to omega times the distance RAB. And this is 2.4 radians per second times the length of the rod, which is 3 meters. So calculating, we get the linear speed to be 7.2 meters per second. So RAB is actually the length or the distance between A and B. Lastly, for part C of the problem, we want to find the angle theta at which the rod will momentarily stop in its upwards swing. So the maximum angle theta is attained when all the rotational kinetic energy is transformed into potential energy. So moving from the vertical position theta is equal to 0 to the maximum angle theta, the center of mass is elevated by delta y, and delta y is equal to dAc into 1 minus cosine theta, where dAc is equal to 1 meter. And this is the distance between A and the center of mass of the rod. So the change in potential energy, delta U, is equal to mg delta y, and this is equal to mg dAc into 1 minus cosine theta. So if we put the values in, the potential energy is the same as the initial kinetic energy, 20 joules, and this is equal to 3 kg times g, which is 9.8 meters per square second, times dAc, which is 1 meter, into 1 minus cosine theta. So the only unknown here is cosine theta. So we calculate cosine theta by rearranging this equation to be 0.32, which gives us this angle theta to be 71 degrees.